And so the first talk in the afternoon session will be given by Dr. Lei Song. I don't know if Dr. Song is here already.
Yeah.
Okay, I'm going to introduce you. So Dr. Song is currently a principal researcher in the machine learning group in the MSRA. His research interests include AI technologies and their applications in industry. So before joining MSR Asia, Dr. Song worked for a leading e-commerce company in China, and where he tried to optimize supply chain management leveraging AI technologies. And he also had plenty of research experience in academia and has authored tons of research papers in several top international conferences. Dr. Song got his PhD, major in computer science, from the IT University of Copenhagen in 2012, and then he joined the Max Planck Institute for Informatics and University of Technology Sydney as a research assistant. So without further ado, let's welcome Dr. Song.
Thank you, Professor Huang, for the nice introduction. So let's start my presentation. So the topic of my presentation is resource optimization in supply chain. So, which is quite a general topic, but I will focus on a case study on inventory management. So as always, so this is not an individual work, but a collaboration with many other fantastic colleges and professors. So before the presentation, so let me briefly introduce the department that I'm from. So this is the Industry Innovation Center in MSA. So basically our vision is to bridge the gap between the theoretical research in deep reinforced learning or reinforced learning between the theoretical research and the practical applications, right? So that's actually our main visions. We want to develop some algorithm, and we want to advance the research in the machine learning and promote its applications in the industry. Yeah. And here's the outline of today's presentation. First of all, I will just give you a very brief overview of what kind of optimization problem we are looking at, and take the supply chain as an example. And moreover, I mean, just to emphasize that our interest is not it's not just in the supply chain, but in general some optimization problem in the industry, for instance, the energy management and many other fields, right? And then I will take inventory management as a case study to see how algorithm look like and what kind of problem we are looking and what kind of challenges that are remaining for the future exploration and so on. So this is the kind of a very high level overview of resource optimization in supply chains. And for those that are not very familiar with the supply chains, actually it's quite a common applications in industry. No matter whether you are a retailer, whether you are a logistician, or whether you are a manufacturer, basically you're more or less will have some challenges in your supply chain management. And here I list a few examples that you may heard or may not. And but even though that we are facing different, this optimization arises from different stage of the supply chain, but more or less they share the same challenges in practice. For instance, the scalability is always a big challenge, right? So I mean, in practice, you often have many different kind of products and many different facilities and resources. How you can assign, how you can optimize your resource allocation, how you optimize the resource scheduling, and so on. That especially given the large amount of constraint and variables, is always a big challenge. And also in the practice, you are also face the quite complex environment and interactions like we call competitive, which is a combination of cooperation and competitive. So it's not only about either cooperation or competitive. There's some usually is some kind of mix. behaviors. And also the dynamic is, the environment is of high dynamic, maybe from the uncertainties of the supplier and demand. So these factors are actually out of control of the company. So yeah, basically you have to assume that there must exist such kind of uncertainty, and you need to have some method or some modules to handle such uncertainties. And also the objective is also, it could be also very complex, right? Not just focus on one dimension, like the maximize the profit or minimize the cost and so on. Sometimes it's a kind of a complex trade-off between many different, like the service level or customer certification and cost and profit and so on. This is another overview of a case study we have already involved in the past years, and basically at least 4 of them that cover the main stage of supply chain from the manufacturer to the last mile transportations. And of course, in each scenarios, we are facing slightly different challenges, but fortunately, we can actually model them in the same framework and using most of the common technologies to solve this. To some extent, not fully solve this problem, but partially solve some challenges arise from this problems. And the framework we are utilizing is called MARO, which I want to promote a little bit here. So MARO is called multi-agency reinforced learning in supply chain and optimization, and it's the open source platforms from MSA, and basically it supports high efficient reinforced learning, or particularly multi-agency reinforced learning. So we, as the other framework, we have some built-in toolkit for reinforced learning to support the various reinforced learning algorithm. But more than that, we have some other components. For instance, the first one is like the distributional toolkits, right? Because especially when you're working with the practical applications, so one challenge, as I mentioned, is scalability. And one way to handle the scalability challenges to utilize the distributed training and sampling and so on, right? So, and we have some built-in toolkit to support such distributed training and so on. Right? You don't need to write code or extra code to have such a function. And basically, you just initialize your algorithm and config and did some configuration in MARO, and you can have the distributed capacities. Another sense is that the simulator building, I mean, because we are working with reinforced learning, so to have to train a policy, right, you have to have a simulator. I mean, it's in most cases, it's not possible to directly interact with the real system, particularly in practice, right? So, and we also support a high efficient simulator, right? The backend of the simulator engine is written in C++, so, and you only need to focus on the simulator, the business logic behind the simulator, and you can take the high efficient sampling or distributed sampling as granted once you build your simulator in MARO. Yeah. Yeah, I think that's all for the general introduction. Let's go deep to the inventory management. So I think today Professor Stroh's talk already mentioned this problem a little bit. So, but since we are working we solve this problem from a slightly different perspective. So I think it's worthwhile to further illustrate what kind of problem we are working. But basically, the basic idea or basic problem is very similar. So the objective here, we want to maintain our optimal inventory level for each product, such that the overall profit is maximized. So here we care about more than one product, you can see that all these products they share the same space or the same warehouse. We are not care about one single product, but they are coordinated behavior as in overall manner. So that's kind of a difference from Professor Zhou's talk. And on one hand, you don't want to overstock some products, right? Because that will bring you extra cost, like the holding, which is the holding cost in the supply chain management. And the holding cost may contain the operational cost from the workers, from the capitals, or even from the space, and so on. And but on the other hand, you don't want to understock some products because that means you will lose some sales opportunities in the future. This is also not acceptable. But these two contradictive objective is kind of our optimization objective. So we want to achieve the best balance between these two phenomena. And of course, the environment, we have certain source of dynamics, right? So the first one is customer demand, which is kind of come from like in some cases unpredictable demands from the customers. And there are some other dynamics that come from the replenish or the supplier, right? So either the policy or either some operator that you tell at each day how many whether we need to replenish for each product and how many, right? And once you place the orders, still there are some uncertainties that may come from the supplier or the vendors, right? Because for instance, if they assume that they can deliver the goods in 2 days, but in many cases, probably this 2 days is just an estimation. It could be 3 days, it could be 1 day, or some other values, because there are some uncertainties from the traffic, from the shortage of materials, and so on. Right? So this causes the whole environment quite dynamic, and this kind of dynamics are in most cases are out of control of the system. Yeah, and as I mentioned, they're often very complex interactions. So we actually the objective is kind of a team reward, or we want to achieve some cooperative or coordinated behavior among all the products. But in sometimes they could be also competitive because they share certain resource, like the storage space, which we have seen here. Right. Also, the budget is also, when the budget is limited, you have to optimize the allocation of your resource to a certain product just to maximize the overall profit and so on. Right, as showing the left diagram. So if the space is the blue box, so that means they have enough space to store all the products. So there's no competition. You basically can view each product individually or independently without care about others. But in case the space is like the red dashed box, so you will have some competition. In this case, you have to balance the storage or balance the resource allocation among all the products. That will cause extra changes in this problem. And of course, there are some other changes like a massive product, which is actually the scalability I refer to. For instance, a very normal supermarket we probably visit every day. They may have more than 20,000 products on shelf, and not mention for some e-commerce companies, they have like millions of products in stock, which will make the problem quickly intractable in practice. So I hope your bonus understands the problem and why we care about it, and what kind of challenges we are facing. So the kind of approach we adopt here is called multi-agent reinforced learning. So why we use multi-agent reinforced learning? And there are some certain reasons behind that. For instance, it's flexible, right? It is sensitive to the change of the product portfolio, because I mean the product portfolio actually in practice is not fixed. It's not static, but it can be dynamic, either because they're out of season or they just don't produce some kind of product anymore or some new product. And also it's easy to model and easy to deploy because you can basically focus on the behavior of each individual product and let the interaction model by some business logic. And also the multi-agent reinforced learning, we have some a nice paradigm to support the high efficient training, like the CD, centralized training and decentralized execution and so on. But of course, there remain some challenges, like the generalizations, which is of course very important in practice, but currently not only in the multi-agent reinforced learning. In general reinforced learning, the generalizations still are very big challenge. And also, particularly for multi-agent reinforced learning, the environment you have some non-stationary because the behavior of each agent are codependent. You have much you will face more critical challenges about the non-stationary, especially when you're training the policies and so on. And of course, the credit assignment is another challenge, especially when you're facing the competitive behaviors and so on. So here I illustrate how we going to partially overcome some challenges in this problem. And we overcome these challenges from two perspectives. So one is the infrastructure. I also mentioned a little bit about the some components in Maro, right? The basically distributed training. We can in Maro you can easily distributed agent policy to different nodes and in a cluster, and we can support distributed sampling, distributed training, and also flexible policy mapping, and so on, just to make the multi-agent reinforced learning training more efficient. But what I want to share more today is actually the algorithm part. So we particularly interested in the massive multi-agent reinforced learning with limited resource, which means that the environment itself has a high extension of competitions, and also we want to achieve a coordinate behaviors. So here I list the two most important challenges, like how to handle the uncertainties, which is basically reduced to some to the spatial temperature forecasting model to solve it, to capture such uncertainties. But this is also not I want to emphasize today. I will focus on the bottom part, how we can independently learn how we can model the competitive behaviors but still achieve the high efficiency learning by decoupling the shared resource. So this slide gives more details about the algorithm, and basically we accelerated the training via the local simulator, which we call local simulator. We distinguish between two versions of simulator. Sorry, I think. I lost my connection.
Wait, I think there is a Professor Chen.
Yeah, there is some
you accidentally share your screen. Hello. It's interesting. Professor Wei Chen.
Probably I can reshare.
What happened?
So I think someone else shared his screen accidentally, I think.
Let's try to reshare.
Someone else is sharing the screen?
Right. Okay. Now.
Okay.
It's interesting.
Right. Yeah. Anyway, so let's continue. So in the algorithm, we distinguish between two versions of simulator, which we call joint simulator and the local simulator. Joint simulator is actually the original simulator where you model all the behavior of the agent of the products, let's say. And but on the other hand, we also initialize some local simulator. Each one of which correspond to a agent. But the agent, the local agent will take extra input from the joint simulator, because the joint simulator is very hard to simulate, very hard to sample data from it. It's kind of time consuming. And local simulator, on the other hand, is support very high efficient sampling, because it's only care about the individual behavior, maybe with limited interaction with other agents. So by such decoupling, we can further accelerate the training and make the massive multi-agent reinforcement learning possible, especially when you have the limited resource. And here I want to say that emphasize that the resource allocations with limited resource actually is not specific to the inventory management problem, but you can find very broad applications in practice. For instance, in the smart grid scheduling, right? You also have the electricity generation component, but you also have some electricity consumption components, and both the supply and the demand of the electricity are also face high uncertainty, and also in some cases these agents need to interact, compete with each other, and also need to coordinate with each other. So this just give you an example how this kind of general structure in practice. Yeah, I think this is just some experimental results, and we can sample. We experiment on scenario with more than 1,000 agents, and we can compare the performance with some traditional algorithm. Like traditional means the algorithm from the OR approach, from the OR approach, or from some baseline reinforcement learning approach. We can compare the efficiency, adaptivity, and effectiveness. Due to the time, I will not spend much time on this slide. So, and we also doing some experiment on some real data from our partner, from our AVT's retailer. So, and we take data from them and to utilize our algorithm to optimize the profit, and we sample two scenarios, like a sufficient capacity and with limited capacity, and so on. You can see that no matter in both, actually both, I remember here the objective is to maximize total profit. So in both cases, we actually achieve better results compared to the current policy, right? In the first case, with the capacity is large enough, actually you can see that we can improve the profit, but with sacrificing certain amount of sales opportunities, because there are many products probably it's better not to sell them, just to make your profit maximum. And another scenario is like a limited capacity. So you can see that it's even more. This is a simulated scenario. It's not a real case scenario. Yeah, so that actually further illustrate how important the coordinated behavior is. Right, it's not important. It's not necessary. It's not enough to just focus on individual agent for the decision making. And this is the last slide of my presentation. Just want to share some more challenging. I mean, we are not yet solved the problem, as still far from the solving the problem completely in practice. So here I just share with you some challenges that maybe will hopefully motivate your future research and force some future collaboration with us. And theoretically, I mean, multi-agent reinforcement still like some theoretical analysis or deeper understanding, right? Here we adopt the centralized training and the centralized execution, but it's still not clear how we can balance between the efficiency and optimality. And in most cases, we assume that to achieve some scalable algorithm, we assume that we also adopt the so-called value decomposition neural network under the assumption of the individual global maximization, the IATM assumption, right? But it's not clear what kind of problem can fit into this scenario, and in which case we can or we can't use this kind of simplification and so on. And also the algorithm, in the algorithm part, right, scalability and generalization is still two most important challenges we are facing currently. We can train and test on the single environment, but whether we can train the policy on some products but still to others, this is also important in practice. But as I mean, so far, and we haven't achieved a good result on this aspect. And also there's some other more complex scenario, right, which more close to the real scenario, like multi-ethno networks, or even more complex resource sharing graph, right? You have multiple resources and maybe shared by a certain amount of certain number of products, not all. And this will make the sharing more complex, and of course the solution more challenging and complex. Yeah, and that's all. Thank you for your attention. And if you have any questions, feel free to visit.
All right, thanks a lot, Dr. Song. So let's see if there are questions from the audience. So I guess I can take the opportunity to ask one question myself. So first of all, what exactly is that local simulator doing? It looks like you're doing more iterations for individual agents, or? Yeah,
I mean the locals. Because here we assume that each agent has an insignificant impact on the overall environment, because like we have a massive agent, right? I mean, each single agent it have very slight impact on the overall environment. So the local environment are just first we let the joint simulator to collect a resource trajectory, right? Using their current local policy, and then by taking this trajectory, the local simulator will use this trajectory as input and sample data for the agent itself, right? In some sense, the trajectory represents the the cumulative behavior of all the other agents. We don't need to care about individual agents of others. We only care about their overall impact, so which can be represented by the so-called resource trajectory here. So that means we can take the other agency behavior, aggregated behavior as input, and also reflect the local simulator just reflect to such aggregated behavior and doing the sampling. That's the view of accelerate your data collection.
Okay.
Very much. Yeah, that's basically the idea of the.
All right. Thanks. So, are there any other questions from the audience?
Excuse me.
Yeah.
Okay. I thank you for your talk, and I saw your GitHub link on your slide. So is this an open source project that I can try on my local computer or Azure environment?
Sure, you can try on it. So there's some built-in simulator and also some algorithm you can try, and you can even build your own simulator using the platform and develop your own algorithm and so on.
Okay, have you are your GitHub repo has a GUI or a command line?
Yes, on the it have the common license. You can feel free to use it. I mean, it have the license, and not. I mean, it's not for commercial usage, but for academic, you feel free to use it.
Oh, okay, thank you
Sure.
very much.